Hi y'all, this is Mel. Welcome back to Heat and Mass Transfer. Today we'll be covering problem 7.021. We are given here, it's a hot day, it's a weather report. We are given a air bulk fluid temperature for air of 90 degrees Fahrenheit. I don't know about you, I don't like Rankine, I don't like Fahrenheit. I had to do that in Thermo too. I'm good, no thank you. So we will be converting to Celsius and thereby Kelvin, which is about 305 Kelvin. We've got a 10 mile per hour breeze out of the southwest. Um, I don't know about you either. I'm still not a fan of miles per hour, so we're converting that to meters per second. We've got bright sunshine, also known as an insolation, our G term of 400 watts per meter squared. This is actually pretty low for sunny insolation, but we'll let it slide. We're observing a wall over which the wind blows, and we've got a length of wall in the wind direction of 10 meters. They give us an emissivity constant epsilon of 0.93, which is how well the wall will radiate away whatever heat it gets. Our surrounding temperatures are 85 Fahrenheit, which is about 302 Celsius. Or not Celsius, that should say Kelvin. Apologies. We've got that our flow is fully turbulent over the wall, and that all our solar irradiation, I should say, which is our G term, is absorbed. This just means that our absorptivity constant alpha R is equal to 1. And we'd like to estimate the average wall temperature at the surface. So we're going to assume, as usual, steady state, quality of life. If you can assume steady state, assume steady state. We've got incompressible flow. We know that the flow, we're assuming also that the flow does not significantly slow down as it passes along the wall, so we don't have any difference in any properties or anything in the x direction, especially for convection. In terms of the incompressible flow, it's air, which is a compressible fluid, but it's moving at a relatively low speed and low pressure, so it's not the worst assumption ever. The flow is parallel to the wall. We're not having any impingement problems here. We can approximate the wall as a flat plate because this is the only thing we know how to do from chapter 7. There's no heat generation within the wall. It's not magical. And we're also assuming the wall is isothermal, which again may not be the most accurate thing ever, but quality of life. So we've got our wall. It's 10 meters long. We've got irradiation over here with the alpha G. Got our surroundings that we're going to radiate heat to. And then we also have our convection, which is going to be just blowing air over the wall. We'll see how that works out. Solution. So it's usually a good idea to start with a surface energy balance, at least tell you how things stand. We know that we're not generating any heat and that the system is steady state, at least we've assumed so. We've got our E in is equal to or E dot in is E dot out. In this case, we've actually got flux. So the assumption I'm going to make here, which it actually turns out to be incorrect, so don't take it right now as it is at face value. The assumption that we are going to make here, or that I'm going to make, which again, incorrect. This is important. I left it intentionally so that you guys can see what happens later. And I can show you later the correct version, is that our heat flux from convection plus our irradiation is what's coming in, and what we're losing is just our heat flux from radiation. So for that, first we need to calculate our H, our convective heat transfer coefficient. A quick note, with a lot of things, you can use film temperature when you're trying to determine material properties or whatever temperature your stuff's going to be at, which is just the average of the surface and bulk fluid temperatures. For this, though, we're pretty close to 300 Kelvin for everything, so I'm just going to call it 300 Kelvin. We know our local Nusselt number. Here's the correlation for turbulent flow, fully turbulent flow over a flat plate. We know that we have to have a Prandtl number within these values. If we steal our Prandtl number from the fluid properties of air, T is 300K. From the textbook, we know that our Prandtl number is 0.707, which does fit in here. We will need to calculate Reynolds number because it's a function of velocity, so it's not just a fluid property. We know here's our definition of the Nusselt number. So if we calculate our Reynolds number, that's pretty high. That's a pretty high Reynolds number, but it's not. Reynolds number is a weird thing because like critical Reynolds number between turbulent and laminar flow happens at different points for different fluids in different situations, so it's not there's not really a hard limit unless you're in like pipes, and even then it's um so with this though, we can say that our Reynolds number is really high. So it's probably turbulent almost regardless of what you're doing. We're going to then, from the Reynolds number, calculate a Nusselt number. So over here we do that, and that's going to get, again, a pretty high Nusselt number. But remember, this is Nu sub x, and that means the local Nusselt number. We're actually looking for the average Nusselt number, or at least the average convective heat transfer coefficient over the entire wall. We do note, remember though, that our average convective heat transfer coefficient is just the average of all the local ones. But since we're assuming that properties and conditions don't change over the wall and that the wall is isothermal, everything should be the same. And if we just integrate that from 0 to L, our 0 term drops out, the L's divide out, and our average heat transfer coefficient for convection is the same as our local. From that, we can, again, make this assumption that if we calculate H from our Nusselt number, we get 10 watts per meter squared Kelvin, which for forced convection in a gas is a little bit low, but it's not that low. It's still like ballpark realistic, so it could work. It could work. We can work at this. And if we do again our energy balance, E in is equal to E out, we should be able to calculate from here our TS. The reason that I used computer modeling for the rest of this is just you don't have to. You can one approach you can take is you can like guess a TS and then be like, oh, it didn't work. Do all the math, calculate the in and the E out. Oh, it didn't work. All right, fine. Guess another one. And that's why I'm doing it with the computer because I don't want to guess that many times. And so here again, we are going to see this assumption that our convective coefficient, not convective coefficient, that our heat in is from convection and irradiation, and our heat out is from radiation. This actually turns out to be incorrect, and I will show you why in a second. So if we hop over to MATLAB, we've got this. This is in MATLAB. Hello, I'm assuming you guys have taken 117. This is our fluid flow convection coefficient. Here's our bulk fluid temperature in Kelvin, surroundings temperature also in Kelvin. We've got our absorptivity, our irradiation. We've got our Stefan-Boltzmann constant, our emissivity. I'm going to assume for starters that the surface temperature is equal to the surroundings temperature, just because that's kind of the minimum threshold where it would be able to radiate heat away from the wall. And then if I say, oh, okay, I'm just going to do 5,000 iterations of this. Let's calculate a couple of things. I mean, we're going to increment our surface temperature. So this is the same guess and check thing. We're guessing a surface temperature, incrementing until we find the right balance. With the first version, I'm going to do what I did on paper with the assumption that our inputs are from convection and irradiation, and our losses are from radiation. The critically important thing to understand from this part is that once your wall temperature, this assumes implicitly that the wall temperature is between the radiation surroundings temperature and the bulk fluid temperature, because if it's above the bulk fluid temperature, it will actually be losing heat from the wall to the bulk fluid. And if it's below the radiation temperature, then it will actually be gaining energy from the surroundings. So this implicitly assumes that the value of the wall is between 302 and 306 Kelvin, which is incorrect, and we'll see that in a sec. So what I did is if we plot that actually, and let me just pull this up, we can see here that our input flux, this is again assuming that we're gaining heat from our radiation, from our convection, which again is no longer true beyond this point, over here where my mouse is. And we can see that the wall temperature has to get really hot before convection, before the convection and the combined with the irradiation is met by the radiation. Like the wall temperature is breaking 350 K here, and it's not even intersected yet. So we can assume that because there was no intersection between, 302 and, there's 302.5 and 306 or whatever. There's no intersection here. That in order to meet our surface energy balance conditions of E in is equal to E out, this is not correct. So what I'm going to do is that I'm going to hop down to this one where I assumed that our input energy is only irradiation and all of our losses are from convection and radiation. We open that one. This actually looks a lot better. We can say here that our heat flux input is just from our alpha G irradiation. That's a flat line because it doesn't change. And then we've got our output of convection and radiation. And as we can see, as temperature wall temp increases, we actually see those 2 points, those 2 lines intersect at around 329 Kelvin. So yeah, that is what I wanted to cover, is that one, because it's not a linear function, it's really hard to extract that surface temperature. And so it's easier to just guess and check. Guess and check is easier with the computer. And once you start seeing results, you can say, oh, actually, that was incorrect. The initial assumption where it was gaining heat from the convection but losing it to the radiation is actually untrue. The wall is warm enough that it's losing heat both to convection and radiation. Yeah, that's it. Thank you guys very much.